And with this, I would like to move towards the student experience part of the event. So we already heard from the lecturers and researchers, and we're moving towards the student experience. And in this moment of the event, I would like to give the floor to my colleague, which I introduced earlier today, Mira Van Nunen, also from the FuseNet Executive Office, and she will be taking over the session right now. So Mira, please, the floor is yours.
Hello, good afternoon, everybody. I would like to introduce first myself. I work at the Executive Office of FuseNet. So if you ask for support when you go on an internship or when you want to go to an educational event, you probably will contact me and get answers from me. And I also work behind the screens with all the events. For today, we want to have two subjects in the master event, and first we want to introduce the winners of the Master Thesis Prize 2022, and after that we want to share student experiences of students went on an internship in 2023 and also of an educational event also done in 2023. So I would maybe give the floor right to one of the first winners of the Master Thesis Prize in 2022, which is Chiara de Piccoli. Chiara, the floor is yours.
Thank you so much. So I share the screen. Okay, I'm not able to share. Maybe I take this time just to thanks on the FuseNet.
It will be solved, Chiara, in a second.
Okay, thank you. I want to thank you for the invitation. I'm very happy to be here. Unfortunately, I cannot stay so long, but then if you have any question, you can write me an email. So, okay, maybe now I am.
Chiara, go ahead, it's solved.
Okay. Okay, can you see my slides? Can you hear me?
Yes, I can hear you.
Okay, so you see my slide, right?
Yes, absolutely.
Okay, perfect. So today I'm going to tell you about my master thesis experience at Consorcio RFX. And with this experience and with this work, I also win the Master Thesis Prize of FuseNet, and I'm really grateful about this. So first of all, I started to explain you where is Padova. Is in the north part of Italy, and in particular, Consorcio RFX is not so close to the center, but it is reachable in 20-30 minutes by bike or by bus. I usually go there by bike. So why did I choose Consorcio RFX for my master thesis experience? First of all, because fusion and plasma was my favorite topics at the master degree. And also for my personal interest in environmental problems. So that was a good choice. And also I do the bachelor and the master in Padova, so I remain there for the thesis. At Consorcio RFX, I found a really welcoming and supportive place where to study and when to work. And there was a lot of people available to help me, and also I have great supervisors. So it was a very good place where to do this experience. Consorcio RFX is the home of the RFX model machine that is now ongoing with the upgrade to RFX Mode 2. RFX machine is a device that uses the reverse field pinch configuration. As you probably know, at Consorcio RFX, there are also the Spider and Mythica experiment that are respectively the negative ion source and the neutral injector that are building for ITER. And there are also research activities for JT60, SA, DTT, and DEMO projects, and also studies on cold plasma for biomedical application. So about my project, my thesis project, the title of my thesis is DTT and the fast particle modeling with Monte Carlo Ascot code. Tommaso Bolzanella and Pietro Vincenzi were my supervisor. In the first part of this project, I first of all learned a lot of things. Of course, first of all, I learned what is the machine for which I have to produce this simulation about fast particles that are injected from the MBI. And this machine is the divertor tokamak test device that is a new machine under construction in Frascati that has the goal to optimize the ITER operation and demo design. After that, I also learned what is a neutral beam injector system and its role in the heating of the plasma, and all the how it injects the particle into the plasma and so on. And of course, I learned how to use the Monte Carlo Ascot code. I'm still learning because now I'm here in Finland to follow a training in the new version of this code. Because after my thesis, I remain at Consortio to do also the PhD. And on this topic, so I'm still working with this code. Of course, this part takes time, but the funniest part comes after. After that, you learn the basic stuff. So the second part of the work was the analysis of the beam-plasma interaction. So when particles generated from the neutral beam injector enter into the plasma, they are ionized first, and then moving into the plasma, they of course give their energy to the plasma particle. So I study how this ionization works. And these are fancy pictures that I put, but of course it is, I don't have the time to go through them. But of course you can find everything in the master thesis work. And so I studied the ionization part and the slowing down part, obtained results that are numerical results. But just to understand how the neutral beam injection work for the divertor tokamak test. Then I use also the constant of motion phase space, that is this phase space that you can see here, to classify fast particle orbit. This was a little bit of a challenge to understand how to interpret this phase space, but was really useful. And again, all the information about particle orbit are reported in the thesis. Here I just reported again fancy picture to show you the possible orbit that a particle can do in a plasma. So we have like passing particle that has this shape, or trapped particle that is this banana shape that is particular, but then there is also like potato shape and so on. And all of these can be classified in this picture, in this phase space here. So now I don't want to be bored, so I also want to tell you something about Padua. I live here for 7 years, so I know some good places where to go. Of course, there are Plaza della Valle, Sant'Antonio's Church, and the Botanical Garden or the Astronomical Observatory. These are my favorite place in reality, but of course there are a lot of other places where to go. Padua is also a city full of students, so there are a lot of things also to do, like drink space in the center, go by bike, try the Pedro Acchis coffee. So it is a really good place where to study, where to do the PhD and so on. It is full of life and student. About FuseNet, I was really surprised about the price, and I'm also really grateful about that. And I want to tell you a funny story about the discovery of the award, because of course I didn't expect it, and the application is done in January, so the price was announced in June, so I didn't think about that in that time. In that occasion, one of my supervisors came into the office, because now I'm doing the PhD, so I remain there. And he told me, Chiara, do you read the email? Do you have something to tell me? And I was like, oh no, I did something wrong, because I didn't receive any email or something, I don't know. And we checked for that incriminated email everywhere, but the spam folder where my email account was hiding these like, dear Chiara, we are happy to inform you that you are selected as one of the winner. And I suppose that when my email account read prizes, it was like, okay, this is a spam, and we put in the spam folder. So, as I already said, I'm really grateful about these prizes. I have to thank my supervisor that helps me a lot in this work. I really enjoy to do this work, and of course, I also to work at Consortium, because now I'm still there. And yeah, just to conclude, I have the moral of the story is that if you find the right people and the right place where to do your master thesis, it's really important, because this could make the difference in your life as a researcher and also in your experience. And of course, the second moral is that you have to check your spam folder time to time, just to be sure that maybe it could contain some surprises. So thank you for listening, and if you have any question, you can text me by email.
Thank you very much, Chiara, for your presentation, and we are also very happy that you were one of the winners of the Master Thesis Prize, and you really did a very nice job. And it's also nice to see and meet you again in the PhD event in the future.
Yeah.
So thank you
you
very much for today, and good luck in Finland.
Thank you
and
so
then
much.
I would like to give the word to Maikel Morren. Are you already there, Maikel? Oh, yes, I see you.
And now I'm also unmuted. That also works.
Okay, Maikel, the floor is yours.
Thank you. All right. All right, so you should be seeing slides now. Is that correct? Yeah, great. All right, so I'm going to talk to you about something about how FuseNet can contribute to your experience as a master student, kind of using my experience as the main example. Well, what you'll typically be doing now as most master students, your program will look like this. You'll follow some courses, you might attend some network or information session events, and eventually then once you're done with the courses, you'll get to do an internship or like a graduation project, a master thesis. And we're kind of now at the second one of those bullet points, and this will likely be the first time that many of you have come into direct contact with FuseNet, but FuseNet can do much more than you. And in particular, at least in my case, the internship was kind of like the golden experience where this could shine. So what did I do for my internship? Well, I went to the National Institute for Fusion Science, which, as you can tell from the picture, probably isn't located in Europe. And it might be a bit vague what is this, but many of you have probably heard about the Large Helical Device, or LHD. And it looks super cool and imposing from the inside, but from the outside, it kind of looks like a big box surrounded by lots of cables and pipes. And what does LHD have to do with this National Institute of Fusion Science? Well, this is kind of the host of where this experiment is. And this institute is kind of located somewhere in central Japan in a little bit of a remote area. So not as nice a place as Padua because it's a bit more remote. But how did FuseNet contribute to this? Well, kind of FuseNet graciously sponsored my stay there, because FuseNet has these funds available for you as a student, which can help you to help fund stays abroad. And what I did for my stay, I became part of the Plasma Heating Physics Research Division, which is based all of these lovely people. And in particular, I was part of a little subgroup called the Neutral Beam Test Tent. And what this group was trying to do is they was trying to make like a new kind of hybrid ion source for the use of neutral beams for negative ions. A typical way you would make an ion source is depicted here. You would pick in some rods and you apply a high voltage to this, and eventually this causes a gas breakdown in the cylinder. Only downside of this is that these filaments, they then get damaged over time. So this would then be unacceptable if you want to use it for a neutral beam, because this would then kind of result in a lot of downtime for maintenance to kind of keep exchanging out these filaments. So another way to generate a plasma is if you use RF frequencies. And both ways you can make a plasma, but then the question kind of is, if you try and marry these concepts, how do the plasmas behave? So if you want to characterize this, you will kind of need some diagnostics. And a diagnostic that's about as old as plasmas is a Langmuir probe, in which case we simply stick in an electrode, we can apply a voltage to this, and then we'll kind of measure what current this electrode is drawing from the plasma. And we can then get these kind of very characteristic IV curves. And we can kind of see some different behavior in there. For example, we can see that there is a region where the current very steeply increases, and it tends to do this with an exponential dependence, which depends on the electron temperature. But we also have regions where the current stays roughly constant, even if we change the bias voltage. And from this, well, what they call saturation current, you can get the ion density, which is the two kind of basic plasma parameters that you'd always like to know. Unfortunately, this kind of diagnostics, it depends on the voltage difference, and it was only designed to work in case of electrostatic plasmas. In case of our case, if we now use an RF source, then we kind of get an additional voltage difference between what's going on at the probe tip and what's going on at the plasma, which is due to this RF component. And because this dependence is so sensitively and nonlinear, unfortunately, this means that if you kind of average out over a couple of RF cycles, this average effect is not zero, but it can in fact be quite severe, especially if the amplitude of the RF voltage is a lot larger compared to your electron temperature, because then it tends to lead to one of the stretching of this IV curve, and it then kind of leads to very fake electron temperatures that you would extract from this if you would kind of only use the blue part of the formula to get the electron temperature. So we kind of need a new diagnostic, and kind of one way which we came up with is since the sensitivity is so it's so sensitive on the voltage difference in the RF component, then we should simply try and make this difference as close to zero as possible. And kind of one way to do this is kind of adding a second electrode to the probe. And in a sense, this is kind of similar to like a double probe ID, where we get a second electrode and we will not bias this electrode. Instead, we'll only bias the probe tip. And then the second electrode, it will tend to sample what is the actual RF plasma fluctuations. And if we then also add a filter to the probe, then these RF voltage fluctuations kind of have to be fed back to the probe tip. And in this way, you can kind of cancel this voltage difference of the RF components. Well, at least that's how things look like in nice diagrams. If you try and make the probe, it just kind of looks like one of those non-super elegantly long sticks. But if you zoom in at the front, we can kind of see this same effect here reproduced in practice, where the large brown part is basically this second electrode, and the very tiny gray part on the top is the probe tip. And yes, you need this kind of ridiculous differences in areas of these two electrodes in order for this to work. Well, how do we know that it worked? We also did some test experiments where we put the probe actually into a plasma, and we extracted some very nice IV curves from this. And we can see that these IV curves, they look very compressed, like the data increases very steeply. And if you try and get an electron temperature estimate from this now, it came at around 3.3 electron volts, which is a very kind of reasonable value for these kind of laboratory plasmas. So kind of all in all, this worked very well. But of course, you don't go like halfway across the world just to do some work. There was also some very nice nature to enjoy, like great foods, nice temples, Mount Fuji, cannot forget this. And if we're talking about Japan, we can of course not forget about giant robots. Also kind of all possible because of the kind sponsoring from FusionNet. Well, so that's kind of has 3 out of 4 of these bullet points covered. And in case you might think, well, shit, my master program does not have an internship. It doesn't have to be an internship. If you want to do part of your graduation project above or your thesis, then you can kind of also ask for the same funding scheme. But there's one thing more about this graduation project where FuseNet kind of, where you can have a relationship with FuseNet, which is different than just a patron and a money receiver. Namely, at the end of every year, as was explained before, all of the FuseNet members, which can be universities or institutes, they can kind of nominate one excellent master student and for a Master Thesis Prize. And of course, I wouldn't be talking to you about this if I wasn't also involved in this. because I also got this nice email with a certificate in it. One thing that you plan to do, if you plan to stay in academia, getting this can be a major boost for applying for a PhD application, which is what I also ended up doing after my master thesis. And also another fun story about the Master Thesis Prize, if you're then like a fresh PhD student, you're attending your first ever conference, it also means that you get to see your face on the big screen of the opening ceremony behind all of the important people at a conference. So very briefly, what did I then do for my thesis in order to deserve this Master Thesis Prize? Well, I kind of looked into something which is called collisional gyrokinetics, using both simulations and theory. Very short, this gyrokinetics is the theory framework that you can use to kind of describe plasma turbulence. And the plasma tends to be turbulent, and we try to reduce this, so we have to understand it, but unfortunately it's very difficult, and therefore people often neglect the role of collisions based on the fact that the collision frequency is much smaller than other frequencies which this theory can tell you that are important for turbulence. But unfortunately, in practice, if you make a discharge, the collision frequency can be small, but it's not zero, so there's always a small discrepancy there. I kind of wanted to characterize how important is this discrepancy. So for that, I looked into one kind of instability, which is called the density gradient-driven trapped electron mode. And why this instability in particular? Well, if you have in the plasmas, we can kind of have these trapped particles, which are located in a minimum of the magnetic field, with collisions can kind of kick those particles out of the trapping region and cause them to become fast particles. So we would expect if there is any influence of collisions at all, it would be most prominent for these kind of instabilities, which depend sensitively on the existence of trapped particles. And there were actually quite some surprising outcomes, because we find that how collisions influence the instability, it was very different for different geometries. Because here we can see kind of the growth rates, so how actually unstable are these instabilities versus the collision frequency. And we can see that in the accelerator, the behavior at low collision frequency is a lot different compared to a tokamak, where there basically is nothing happening. But also interestingly, in both cases, we find if we go to very high collision frequency, we kind of expect the growth rates to go down because we have less and less trapped particles. But we can find that this exponent then tentatively depends on the collision frequency, which was something that actually the literature thinks they should all be the same exponent. And well, this was very brief. Now that I've done my part shilling for FuseNet, I can also do some shilling for myself. If you find this is very interesting, then keep an eye out on the archive, because I think in a couple of weeks, a paper about this, you can find it on there if you want more information. And with it, I'd like to thank you for your attention.
Thank you very much, Maikel, for your nice presentation. And yeah, there was a lot of information in there. So I think everybody was very nicely educated on your thesis and also the lovely experience in Japan. I would ask Tobias Peherstorfer if he is available already for the final talk about the Master Thesis Prize winners.
Yeah, sure. Can you guys hear me?
Yes, we can.
Perfect. Okay, let me just quickly share my screen, and then we should be good. Up. Okay, so hi everybody. My name is Tobias Peherstorfer. I am an Austrian student from TU Vienna, and I was the third person to have the honors of getting this FuseNet Master Thesis Prize in 2022. And I'd also like to first bring you, like kind of give you an impression of my own personal fusion journey, kind of, and to also tell you a little bit about my master thesis in general. So on my fusion journey, as I said already, I am studying at TU Vienna. I started my master's in physics there, and in an internship, an Erasmus internship, I got to the Institute for Plasma Physics in Garching, Germany. Also, often I will probably call it IPP because I'm so used to that. Where I met also my thesis supervisor, or to-be supervisor, which was super nice. That was right before the pandemic hit, so it was very cool that we were able to still make the internship in person. That worked out very well, and I got kind of to know a lot of plasma people at IPP, and got to really enjoy both the topic and the community. So I then decided to apply for a, first of all, then this internship went very well. I started my master thesis at IPP in collaboration with them. And I also applied for the Plasma Surf summer course in June 2021, which was really cool. It was funded, also co-funded by FuseNet. So as it is a very cool educational event that gets you very close to other students in the field, that gets you familiar with a lot of different plasma physics topics that you otherwise would never get in touch to. It's a great thing. So I went there for 1 week. It was super nice. Also, Lisbon is a very beautiful city. And then finally, when my master thesis was basically finished, I also got the opportunity to present it at a conference that was also held in Garching, Germany, on the Runaway Electron Modeling meeting. Yeah, so all in all, I met a lot of cool people in this community. Really loved it. So I'm also extremely honored to be awarded this prize for my master thesis. I honestly also didn't really expect that. It was kind of a surprise. Okay, just to give you some more impressions on what it was like in all these locations other than the world map. Of course, in Germany, I met a lot of interesting, cool colleagues like Paul over there. I saw a lot of impressive looking machines, a few pieces of weird German architecture that I was probably not savant enough to understand. Then I found this video where for the first time, I probably recorded the first time my master thesis code actually worked. So that was nice, at least for me. Since I not only enjoyed the company of a lot of cool people in Garching, I also enjoyed the various features of German life, with very Bavarian food and some beer in nature, which was nice. I also talked briefly about the Plasma Surf summer course, which was a great experience because basically you meet people that are all in the same boat as you, which is great. You can really connect with all of them. You learn tons about plasma physics in different disciplines. Also, you have a lot of fun outdoor activities to do. So we went rock climbing by the sea, which was super nice. We also went surfing, as the name of the whole event kind of implies. Now, I didn't find any really good pictures of us surfing, but you can imagine that it looked somewhat like this. We were very professional at this, as you can imagine, for first timers. Yeah, it was nice. So, after giving you some impressions, I'd briefly take you through the master thesis, what it was about. The title is Fragmentation Analysis of Cryogenic Pellets for Disruption Mitigation. Very fancy title, but what is it actually about? So, first of all, what is a disruption? In tokamaks, there's a lot of energy in the plasma, right? There's thermal and magnetic energy, and a disruption is any event where an instability in the plasma grows so much that it causes this huge energy of the plasma to be lost to the vessel wall in a very short time scale. So this can produce high thermal loads, strong electromagnetic forces on the vessel, and it also can lead to a beam of relativistic electrons that move around in the tokamak and then hit the wall somewhere, as you can see on the right here. They even can severely damage these very high resistance beryllium walls. So this is a phenomenon that occurs is more prevalent the larger the reactor gets, and also the more energy is in there. For example, for ITER, this will be a very relevant problem. And this is also why a lot of research is also going in the direction of how you can prevent and mitigate these disruptions. And this is also what we looked at in the project that I was part of. So you can deal with these disruptions in the way that you can mitigate the damage they do. So whenever an instability comes up and is detected, you can shoot material into the plasma, and this material then dissipates by means of line and radiation and Bremsstrahlung the thermal and magnetic energy of the plasma kind of isotropically along the wall, and prevents basically this very short time span high energy transfer of energy to the wall. And in the experiment in the technique that we investigated, we had something that is called shattered pellet injection, where you from the right you kind of freeze a pellet of gas to like imagine it like a corkscrew of frozen neon or something, and you shoot it with very high speed towards the plasma. Shortly before entering the plasma, you break it apart so that the surface of the pellet is larger and it ablates evenly kind of in the plasma. And that material that you shoot in is then supposed to mitigate this disruption. Now, how exactly this pellet breaks apart is pretty hard to model and to predict because it's a very weird material. It's very brittle. But in order to make efficient simulations for predictions in ITER and other large-scale systems, you kind of need to know how large they will be, and because you want to know how well you can mitigate which kind of disruption. So what we did in Garching, we built a test setup for this. We build a setup where we can freeze these pellets, and we don't shoot them into a physics reactor, a fusion reactor, but into a vacuum test chamber. And the focus of my thesis was basically to look exactly at what is going on there and to categorize how these fragments shatter. So the general thesis idea was, okay, we measure the fragmentation that we can observe in the experiment. We compare it with the one literature model that exists. And we prove it either way, because if it's good, well, we know the literature model is good. If it's bad, well, we have just made a very important discovery, right? So yeah, just to show you what these pellets look like, or can look like, on the left-hand side, you can see a very, very slow-moving neon pellet that didn't break at all. And on the right-hand side, you can see a very fast deuterium pellet. Just for time scales, these videos were recorded at 30,000 frames per second. So these things are really fast. Could probably shoot a hole in a wall with these pellets. Anyway, the approach I used in collab with my supervisors to get the information of the fragmentation out of these videos was a Python-based computer vision algorithm. So we fed into this algorithm the raw images, and it got us to basically segmented videos where each of the individual fragments that was detected was measured in size and velocity for each frame, and also identified with each other so we can follow one particle along. I'll go through this briefly. You can divide the algorithm into 3 steps, which is the pre-processing, the background subtraction to detect the fragments, and also the fragment tracking finally. Pre-processing is basically just make the fragments more visible. So you apply some image transformation, some smoothing, and filter out sources of noise. In the second step, you make a statistical model for pixels in the background of a video and compare subsequent pixels to one another to get out which of the, if in one frame, the pixel intensity is very different from usually, then you can assume that is basically not background anymore. I did that, for example, using a Python library that's called OpenCV, but you can probably do that on your own as well. And finally, when I had these outlines of the individual fragments, I started with fragment tracking, which is basically just matching these outlines in the individual frames together and making sure that we can sit on one pellet and follow it along the flow. Okay, this was basically how the application worked, but what's maybe more interesting is also the results. As I said, we compared these results that we measured here with theoretical predictions of a model. And I mean, this is a 4 plot, so I'll take some time to explain. On each plot, the x-axis is the normal impact velocity of the pellet, so how fast it hits the tube band before it breaks. And on the y-axis, you first have the mean fragment size for each individual pellet and the number of detected fragments for that same shot. The colors just denote different shatter angles, but these are not so important now. What we found out is that actually the theoretical model does not describe the same trend in the data of how these pellets fracture as the fragmentations we observed in the experiment, which was very relevant actually for ITER. So yeah, it was a very cool thing to do, and it was also nice to present these findings at the conference. Yeah, so that is basically the main outcome of my master thesis. That is scaled differently, and of course a valid input also for other simulations that follow with this disruption mitigation. And that's also the end of my talk. And I'd like to thank for sure FuseNet for allowing me to talk here, and also my supervisor at IPP, at TU Vienna, and also the organizers of PlasmaSurf, because that was really great too. Okay, thanks.
Thank you very much, Tobias. And to all of you, Tobias, Chiara, and Maikel, congratulations again on winning the last year's prize. And just to announce to everybody else, look at the website from the 1st of December 2023. The new call will be open for the Master Thesis Prize 2023. So maybe you'll be there, one of the winners next year.